Welcome to the Wireless Communication Alliance Wireless Power Transfer webinar. I'm Jeremy Toll, Vice President of WCA, as well as Director of Research and Development at Asbill Corporation, who is a sponsor of WCA. We hope you and your families are doing well and staying healthy. As this is the first webinar that WCA has hosted, we're excited to be able to reach a larger audience through this format and are planning additional webinars in the future. We would like to extend a special welcome to our international guests, as well as guests outside of Silicon Valley. Additionally, since we were able to extend our geographical reach, my mother is able to attend her first WCA meeting on a very special day. Happy birthday, Mom. We're excited to announce that industry partner IoT Nation is offering free use of its IoT market intelligence platform called IoT ACE database to the WCA community through May 31st. This platform allows you to search 25,000 IoT related companies, use cases, webinars, events, contacts, and more at www.iotnation.com. To access this, use sign-up code WCA100. We would also like to thank our sponsors, Google and Asbill, along with our event sponsors, Energous, ETI, and Everactive. As we are a nonprofit, we appreciate any and all support through donations of money, venue space, and volunteers to help provide valuable events to you. And here are a few housekeeping items. We ask that you keep your microphones on mute. Since this is a large audience, we're asking during the webinar that you submit questions via the chat feature in Zoom. We will try to answer as many as possible in the time that we have. Wireless power transfer holds the promise of freeing us from the tyranny of power cords. This technology is being incorporated into all kinds of devices and systems. The concept of transferring power without wires, however, has been around since the late 1890s. Nikola Tesla was able to light electric bulbs wirelessly at his Colorado Springs lab using electrodynamic induction, also known as resonant inductive coupling. With increasing interest in autonomous and smart systems in various vertical markets, such as smart home, smart factory, electrical vehicles, etc., wireless power transfer has become a must-have technology that will enable convenience, mobility, and efficiency. Wireless power transfer technology has been around for decades to a century, but now the technology is able to be commercialized in practical applications and has the promise to directly impact mankind. The Wireless Communications Alliance invites you to listen as a selected panel of experts explore how wireless power transfer will transform our lives. Our extraordinary panel of speakers assembled for you today include Jeff Yen of ETI, Etherdyne Technologies, who will provide an overview of wireless power technology. Niraj Sahejpal from Energous will talk about short and long range RF wireless power and energy harvesting. Mark Montrose from Montrose Compliance Services will discuss EMC, electromagnetic compliance and certification. Rosita Taymorzadeh of Asbill North America Research and Development will provide an industry use case for industrial IoT. And Shadi Hawawini from Everactive will discuss energy harvesting. So first, I'd like to introduce Jeff Yen, who's the CEO and co-founder of ETI. Dr. Jeff Yen got his PhD in physics searching for dark matter. As a trained physicist, Jeff has a strong entrepreneurial mindset that made him embark on a journey of business and co-founded a company that is doing wireless power. He's co-author of multiple IEEE papers and co-inventor for 15 patents worldwide. And Jeff, go ahead and share your screen, please.
Hi, everyone. So I assume you can see me and see my slides. So thank you, Jeremy, for the introduction. And thanks for Peter for the, for the invitation for me to be here today. So everyone, my name is Jeff Yen, and I'm very excited to talk to you about wireless power today. And I will just give a very high-level overview of all the wireless power techniques that exist today. And also the rest of the talk, there will be multiple speakers that will talk about other aspects of the wireless power industry, including market, applications, and regulations. So I will start by talking about the vision for wireless power. So I think the goal is to achieve a seamless human-machine interaction. So the machine here really means your phones, your cars, everything that require some sort of an energy source. And then one of the example I usually give, I love the most, is actually the Iron Man movie, where there's a human-machine interaction so seamlessly. So obviously, the ultimate goal for the mankind is actually to do ultimate human nature integration. And for that, can only go refer to the Master Yoda, where he can use his mind to actually move things around to do his will. So this is obviously is something that we all want to do, but we are far away from even realize any of that. So as Jeremy just described, actually the wireless power concept is not new. In fact, Nikola Tesla was the first person to try to embark on this path. He has a vision of a wireless power the whole world that provide free energy to everyone in the world. But he's too advanced, and he's obviously ahead of his time. So the project didn't go further too long before he ran out of money. But after that, really, a lot of the majority of people are focusing on the microwave beaming power, which is one of the most milestone that has been achieved is back in 1975 with a NASA JPL Goldstone. So what they have been successfully delivered 30 kilowatts of power through a 1.5 kilometer long of a distance using 2.4 gigahertz. So that was in 1975. So this is still by far the world's longest and the most powerful energy transfer today. So since this wireless power has been developed and to demonstrate for so long ago, why are we talking about this today? Because today we have an increasing more and more battery powered devices that connect to the internet. That actually makes the whole thing increasingly harder and harder to maintain the battery, to replace the battery, to charge the battery, and just using wire. So the fact that the number of the batteries that you need to maintain in a household or in anywhere is actually getting so prohibited that actually intentional wireless power is required. So in order to charge a battery, there are multiple ways. So the next slide I'm going to show is energy harvesting. So it's a natural way that I think about how you actually charge a battery, which if you can just gather ambient energies like the one I listed on the left side of this slide, which there are 6 different categories of energy source that can be harvested, that actually go through a device to transform this energy into the things that you need, like charging the battery or like just directly provide power. Now, this is all good, and but the thing is, there are a lot of great applications that come out with the energy harvesting. However, if you need something that is more powerful, then you have to turn to intentional wireless power. In the energy harvesting, we will have a speaker later that will actually talk about his company and how they use energy harvesting to actually do a real life application. So that'll be cool. So I have there is a frequency used for the wireless power. So this is something for the audience that is more familiar with the WCA. We are in the frequency space. So I have at least 5 different types of wireless power to use, and draw its associated frequency that used. So on the far left is ultrasonic technology. So ultrasound is something that you actually have a mechanical vibration through a medium. So those medium can be something like air, like a concrete, like a metal, or even just like human body. In fact, one of the most used ultrasound technology to do wireless power is a medical use for the implants. So it is something that has been known as has been explored. So however, if you are delivering energy through air, ultrasound does impose certain physical difficulty. So in order to achieve that, there's many more things need to be overcome. So the second item I list here, which is a magnetic induction. Magnetic induction is something I think everyone here probably know the most. In fact, all the recent wireless charging for cell phone are all using this technology with the magnetic induction. But this is actually also being used like an electric toothbrush. So there are multiple consumer electronics that you can see today that are using wireless power are basically just from this magnetic induction. So the third item is a magnetic resonance. So magnetic resonance is actually a newly emerging technology that was actually initially developed by our co-founder and the chief science officer, Dr. Robert Moffett. So when he was back in MIT, this is actually one of the inventions that came out with that institution and later become the industry standard for charging, and now it's for electric charging vehicle. So the next item is the RF beamform. So this is actually quite exciting field. There's decades of experience and study on the RF beamforming. And in fact, one of our speakers later, he will actually talk about exactly these 3 different frequencies that's being used for a different type of a distance and applications. So that will be quite interesting. Now, the last one is the infrared laser, which is something that people know less about, but this is nevertheless is actually a very exciting technical development. So in fact, this a newly innovated technology is actually using the transmitter and the receiver as a 2 lenses that actually form an external cavity that actually amplify the photon. And they use the photovoltaic to collect those infrared energy to convert it to electricity. So it is a very interesting technology, but I don't really have time to go through in detail. So I will just leave as that. So this plot I show here is actually a wire carrying current. So you can see there is a pattern of electric and magnetic field that actually form in this region. One thing I want to mention for those audience who are not familiar with this, electromagnetic field are basically contains energy travel through space, and they are pretty much is what the wireless power is made of. So in general, you can segregate into 3 different physical space for this. You have the one near field that is actually closer to the source of the origin, and you have a far field, which is actually furthest away from the source. There's a very interesting zone, which is called Fresnel region. This is actually where a lot of beamforming technology and a lot of study has been doing, because this is where you can concentrate energy and to do very interesting wireless power. By the way, so for those of you who are not familiar with Fresnel, Fresnel was a French physicist back in the 18th century, and he was the first person to develop a composite lens that actually developed for the lighthouse. So with that being said, the far field usually the people become just irradiated. So that means it's more suitable just part of energy harvesting. And there's a Fresnel region, which is where beamforming is, compared to the near field, which is what induction and then magnetic resonance use. So this is a slide about the wireless power safety. So I think this slide is particularly suitable for the electromagnetism. So if you are talking about ultrasound using the air, there will be a different safety regulation. If you're talking about laser, part of this is required, but also there's a different form of a laser safety compliance that has to fulfill. But the point of showing here is not go through the detail of what each item means, but it is something that I would like to emphasize that for the past 20 years, there are multiple tremendous amount of research getting into the safety of the electromagnetism and how that interact with the human body, and how does the human body interact with all this type of different electromagnetism. So the safety is always the top priority for all the players in the wireless power space. Whenever we design and to think about a product, this is always the first thing that we actually comply with and to develop. In fact, many different technology of a wireless power has a different range of a power level with a distance they can deliver. Is mostly are actually set by the rule of the safety. So I just want to emphasize that. So with the last 1 minute of my talk, I would like to give a demo of the near field magnetic resonance as my conclusion. So this is a 5-watt lights that actually can move around in the table and underneath the table, and you can turn on and off just by flipping them. And everything here is still considered near field, although the distance is actually quite significant here. So all of this is a small marble are wireless power with no wires and no battery. And it is freely to move around. And it has a different intensity and the dimming and everything is actually by design. So this is actually a small motorized device that actually can be placed inside this near field zone to show, you know, the different power level can be achieved while in the space altogether. So I will actually post here and finish my overview and give it back to Jeremy.
Thanks, Jeff. That was very informative, very interesting technology. I hope people enjoyed that talk. Question for you, Jeff. In your vision, the slide you showed about vision for wireless power, you mentioned a seamless human-machine interaction. Could you elaborate a little bit more on that?
Yeah, I think that one of the things about this in my mind is that, you know, how the history has evolved itself. Because before we have an electric wire in the household, light bulb is actually pretty much the first thing that we thought about doing. But once you have electricity in the household, then there's a whole type of different product that comes along. You know, like your refrigerator, your microwave, your toaster, you know, they are all actually a byproduct of the fact that you have electricity. So I do think in the future, if the wireless power is everywhere, just like a Wi-Fi today, imagine that, then you can actually create a whole source of different products or different things, I would say. That's why I say the human-machine interaction, because you can actually interact with a lot of electronic devices without knowing you need to actually put a battery, without knowing you need to, you know, put a wire. And this will actually create a whole new world, I would imagine.
Yeah, that sounds great. Well, thanks. Next up is Niraj Sahejpal, who's the Senior Vice President of Marketing and Strategy at Energous Corporation. He's responsible for corporate strategy, product management, and driving customer and strategic partner engagements. Niraj holds a master's and MBA from Santa Clara University. And Niraj, please go ahead and share your screen.
Thanks, Jeremy. Thanks a lot, Jeff. I think that was a great presentation. Let me share my slides and then we'll go from there. Can everybody see my slides?
Yes.
Okay, good. Okay, brief note about the company I represent today. First of all, thank you, Jeremy and WCA, for the opportunity. We're a small company based in San Jose, California. We are focused on RF power, which is a subset of what Jeff presented. By the way, Jeff, you know, amazing, and think I agree on most of the discussion you gave, and I'm going to focus on the RF part of your presentation. In a big nutshell, we are a fabless semiconductor company where our goal is to sell chips. We have done chips in all the frequencies which Jeff talked about: 60 gigahertz, 24 gigahertz, 5.8, 2.4, 900. During my talk, I'm going to talk about a little bit about the different pros and cons of frequencies and what are the challenges in front of harvesting. And I think where there's a lot of limitation that is coming, and industry has to come together to find solutions. Energous is also known for first power at a distance, Part 18 approval under FCC, which we got in December 2017. That was for a 3 feet, 174 milliwatt, where monitor was charging keyboard and mice. Today, we are approved to ship in 112 countries, especially EU, North America, and Japan. So our vision is, same with Jeff, the Wi-Fi should be as ubiquitous as, wireless power should be as ubiquitous like Wi-Fi. It's going to go through a transformation and evolution, which we're going to see, and we're briefly going to talk about. So let's just step back and think about what does it take to launch a new technology, especially the RF technology. Multiple forces are happening which defines what the roadmap of a technology would be. And understanding that is very important. As Jeremy said, and Jeff also mentioned, this is not a new technology. All the time, there were two major constraints why this has not really taken a mainstream so far. Well, first one is commercial viability. What does commercial viability means? The size, power, the cost, and the application of that in terms of consumer mindset. The second is, can you prove it is safe? Once you start applying these two forces on what is possible, you start to get into what is possible today, what may be possible tomorrow when these conditions are relaxed. In this chart, what I'm showing is that the wireless charging is the cusp of these three forces, where the customer application and requirements are talking to the technical capabilities of the industry, and when they are constrained with the regulatory. The intersection of this is actually what is possible today, and more roadmap will be possible when these three forces start to interact more and more. RF is different than any kind of a tightly coupled like inductive or loosely coupled like resonance, that you can charge multiple devices. Orientation freedom is more, and you can actually go from a smaller distance to more distance. It's an E-field technology, not unlike the coil technology, which are H-field, which is a major difference in terms of foreign object detection, 90-degree charging. And now the challenge is, all that is good from a technology standpoint. Can you make it viable? And that's where semiconductor comes in. That's why when 2014, we were looking to start this whole initiative. We want to make sure we focus on that. So Energous, we have been kind of thinking about how to really frame the RF power. This is a chart that should clearly define what I mean by that. On x-axis, we talk about the distance. It goes from 0.5 centimeter, 15 centimeter, 1 meter, 3 meters, and 5 meters and beyond. On the y-axis, we talk about the power. The power is to the receive power that is at the battery of the received device. If you start to look into the various kind of opportunities, you see the small sensors here, which is less than 10 milliwatt, 1 milli, in some cases microwatt and nanowatt also. And then you talk about hearing aid, which is 50, 60 milliwatt. Then as you go higher and higher, you start to go toward phone, industrial devices, cars, and so on. But the distance is something interesting. A typical, the typical application of RF power is actually a link budget exercise. In fact, the farther you go, the more the dominant force happens because of the path loss. That's a distance between transmitter and receiver. And we start to kind of not understand that while we start to talk about various power levels at various distance. In our opinion, you're going to go farther and farther. The power is going to go lower and lower because you're constrained by the regulatory regimes which are available today. And from Energous perspective, we have gone into an incremental roadmap. We are starting from a small power, small distance, while providing all the benefits of RF like angle charging and multiple charging. And then we are going toward smaller power because we have efficient receiver technology. So this, let me just stop here and talk about the challenge of harvesting. Then we talk about the energy solution that we are in the trial with many customers worldwide. The harvesting, in the sense, like, it can be defined into two areas. Most of the harvesting when people talk about is something called ambient harvesting. That means there is a power available in the band. I just put an antenna in that band, 2.4, 5.8. I should be able to get the power. But what everyone misses is the amount of power you get is extremely small. You think about the power your phone receives from a cell phone tower or a Wi-Fi AP, they are in milliwatt, less than milliwatt. Once you convert that into a DC and go through a DC to DC all the way to the charging, you're talking about microwatts of power. That might be okay for small sensors, but they're not meaningful in many ways. So ambient power has an application for small sensors. Yes, it is cost effective because you do not need to worry about the transmitter. You're just harvesting what is available. The other way to look at is a smaller space where you actually deploy a transmitter in a band and you get higher power in this case. We believe at Energis, more and more application will move towards that mode, where a small transmitter will be deployed and a receiver will be able to get more power, more in the range of 10 milliwatt to 15 to 20 milliwatt. Our receiver technology can go all the way to minus 20 dBm. So we can harvest also in the band, and our harvester actually can go from 2.4, 5.8, and 900. We have the harvesting chip available in all three bands. Most of the application which we are seeing, they fall into either smart home category, like a security cameras. They require more power, but they need to be charged at a distance. Then you start to see electronic shelf labeling, which is a significant market under development right now on the retail side. Then the enterprise, storage, warehousing, and industrial. Industrial is a very interesting market. Most of the robotic arms, they would not like to have wires hanging around because that limits the freedom of movement. We start to see a lot of application, but if you see one common thread, yes, they would like to charge at a distance, but the power requirements are different. And that's where my summary is. If you look into the harvesting today, I think there's a lot of interest in harvesting, but we are still not there to understand the requirements. So number one problem in front of a harvesting market, or as I call it, transmitter receiver harvesting, is the application. We need to understand the application very well. We need to understand whether the application device is small or large. We need to understand whether it's microwatts requirement, or is it like a milliwatts or in a watt of requirement. And then we need to start segmenting those markets into different kind of RF technology or even non-RF technologies. We also need to understand whether the application is outdoor or will it be indoor. Very similar to Wi-Fi and cellular split on the connectivity. If you're looking to outdoor, for example, putting sensors on a pipeline, those may not be RF kind of technology. Those might be maybe solar or other kind of technology. What that means is when you have these devices, they're coming from outdoor to indoor, they may require a handoff from a non-RF to RF technologies. These kind of architectural decisions we need to think about. We need to think about the silicon solution that will provide those kind of things. Similarly, the frequency, whether it will be 2.4, 5.8, 900 or something else. We need to think about, would it require multi-band harvesting where you can keep on switching to the frequency where you get the most power. These level of decision making is not available today. We're only looking into harvesting from a perspective of opportunity and not really seriously thinking about how would this be deployed. Similarly, the power profile, receiver power I talked about, but would the power be required in a continuous way? Or will it require, for example, sensors? Why do you need to power sensors every hour of the day? You don't need. You need to think about a duty cycle approach, where rather than having a battery or charging technology, you might be putting super cap technology, where you charge it after a certain time, it sends the data, which might be sufficient for. My point is we need to think about these design and architecture challenges and come up with a silicon that will address them. Then only the real value of harvesting market will be achieved. Thank you very much, Amy.
Thanks, Niraj. I appreciate it. I think you answered a lot of my questions. One that's come from the audience, though, is actually, could you elaborate on different energy harvesting challenges between commercial home applications versus industrial applications?
I think I would say more like challenge is the opportunity. I will.
Well spun.
I think if you think about RF, I'm going to focus on RF. Definitely, there is a lot more discussion on the non-RF opportunities. In the RF, the regulatory constraint is very important. In the industrial use cases, it is possible that you may not be limited on any kind of transmission because there is no NMET, and these are controlled environment. But that is true about defense and the public safety also. What that means is you may be able to transmit higher power, and you may be able to get higher power on the receive also. A smart home is a very consumer cost sensitive kind of market. I don't think so. You can actually get an ambient kind of solution in smart home, because the amount of power those devices require will not be met through a ambient harvesting.
Okay, great. Another question is, do you anticipate any potential interference issues with other devices operating in like 915 megahertz, 2.4 gigahertz, or 5.8 gigahertz bands?
So good question. So say regulatory, we talk about transmission, talk about receiver absorption and the coexistence, right?
Right.
If you're only doing an ambient, you're not seeing any kind of these issues, because emission is not there. Emission is a transmitter property. Absorption is also dependent on the transmitter. So in the case of ambient, these issues are not there. In the case of a dedicated transmitter, it really depends upon how you generate the signal. I believe in 2.4 and 5.8, you're going to see more coexistence issues. For example, 2.4, there's a narrow 60 megahertz band, and there's so many other devices. Similarly, 5.8. In 900, there are less and less devices. And for example, our technology, we use a very narrow signal, and we are able to coexist with all these devices. By the way, coexistence is one of the tests that you have to pass to get any regulatory approval.
Okay. Sounds good. I appreciate it. Thanks, Niraj. And people may put in some other questions that we can have you answer in the end with the whole group. So thank you very much. So next up is Mark Montrose with Montrose Compliance Services. He's a principal consultant at this company. It's a regulatory compliance firm specializing in electromagnetic compatibility with 40 years of experience. He's assessed as an EMC test laboratory for in situ testing of industrial products, providing consulting and design services for any category or application of electrical products. He has authored numerous technical papers, several journal articles, and 5 textbooks on EMC, his latest titled EMC Made Simple, Printed Circuit Board and System Design. So Mark, without further ado, you can take over the screen.
Okay, very good. Thank you.
Yep.
Okay. Well, thank you for having me participate in this webinar related to compliance with EMC. I'm going to be focusing more on the regulatory aspects of what we have to deal with on the EMC side. Later on, depending upon the time, we may go into some areas of product safety. Okay. So let's take a look at what is the requirement for wireless devices. Anything operating above 9 kilohertz has to be tested to and comply with international regulations on a worldwide basis. There are very few exceptions for wireless transfer, and that will be seen on the next slide. But when we get into the regulatory, the RF world of compliance, we have to worry about what is the device, and does it have intelligent communication, or is it just passive charging? Okay. All right. The FCC has a database known as KDB 68016, which this material is extracted from for ease of presentation, and I like to use a lot of verbiage to help everyone remember after the fact. Anything that creates energy has to be approved on an international basis, except for the following: high power devices, devices used for power transfer at a distance. Now, this is not the beamforming. Magnetic resonant devices, these are your MRI machines commonly used in hospitals, and also certain types of medical devices. Okay. Right. I'm just having some weird things with my screen here. So anyway, intentional radiators or unintentional must comply with Part 15 rules and generally require equipment certification. It can be self-declared, or you can get tested through an EMC lab to issue your report, and you can self-declare. But that is an exception, mainly certification. So there's two types of devices, one that does charging and one that does communication. You may have to test to Part 15 or Part 18, or maybe even both, depending upon the operation. If you're just doing wireless charging a battery, maybe determining what the level is, that's a Part 18, which is more for industrial, scientific, and medical. However, if you transmit any intelligent information, such as, are you on? What is your power level? What is the status? Any kind of intelligent information that is transmitted must go through Part 15. Although we talk about a single product, we have to take a look at what is its application and that little transmit module within the end-use host system. You may have to test it for unintentional transmitter, Part 15, if it's a system device. And then you may have to also test it for the intentional transmitter part if you're doing communication, or just Part 18. Transmitters and receivers are generally approved, separately, but they have to satisfy both standalone and as a system. Many engineers think that, oh yes, I'm going to just get my device approved and we're done. But what if that gets installed in another host system and receives power from that host system? Then it has to be approved as an apparatus or part of that system in order to be officially certified. Receivers have to be approved as part of the host device. If you want to go the easy way, Part 18, you must limit the communication to only power control and load management. Now, the specification limits are essentially identical between the two standards. It's just how you categorize it. So with Part 18, the load and power management must be integral to all power transfer at operations and all frequencies that it may be used in. If you use it at 2.4 or 5.8, you have to test it at 2.4 and 5.8. We also have to take a look at what is the distance that we are communicating for, if all the energy is in the near field, or if we are getting into the far field for intelligent communication, because intelligent communication falls under the category of something like information technology equipment. The Part 15, Subpart B, are for those devices that are utilized within an apparatus or a system that does not have information transferred between the items, between the wireless devices. Part 18 is, again, for non-intentional. The considerations, as you can see, everything must be evaluated in a end-use product. Testing, the worst case, has to be done at full power, and we've also seen situations to where at minimal power, problems can arise due to resonances that exist between charging coils. Although this is the last slide I have on the EMC, it requires a considerable amount of elaboration. There is a new directive out called the RED Directive, Radio Equipment Device Directive. We have to comply with the EMC directive. However, if you have any transmission of any intelligence using the radio frequency bands, then you have to declare it under the RED directive. The tests between EMC and RED, they're exactly identical. So if you write a technical file to describe your system, instead of putting 2014-30 EU, you put on 2014-53 EU. It's the same, just how you describe it. So this is for communication devices, because anything that transmits a signal is considered to be an intentional transmitter. Now, when we get to the international world, we have the ETSI standard, European Telecommunication Standards Institute, and here's a number of the most commonly used standard, and this is the title, and you can read it. If you go to the ETSI website and you type in wireless charging or wireless power, you'll pull up many different standards. If you type in wireless, you will get hundreds of standards. So I recommend if you do a Google search under the ETSI website, you get the appropriate one. Now, the big difference between the FCC and Canada, which is harmonized, and Europe is not just the emissions. Europe and many of the other countries require testing to immunity standards. And the discussion of immunity is well beyond the scope of this presentation, because most wireless devices really do not get affected by power line surge or fast transients, voltage variations from the power supply, radiated electric fields, or line conducted emission or line conducted fields. Possibly magnetic field disruption is a possibility. So you may only test to that. So Europe requires emissions and immunity. Many other countries in the world require emissions and immunity. North America requires only emissions. And that wraps it up for a real quick overview on compliance related to the EMC, or electromagnetic compatibility aspects of wireless charging devices.
Thanks, Mark. Appreciate it. You made a pretty complicated topic a little more reachable for people. One question is, people are concerned about safety of wireless devices in general. There's like a lot of concern about 5G these days, but I'm sure once wireless power gets more common, people are going to be concerned about that too. Do you have any thoughts on how to, or what's being done for safety compliance, and how to make people a little more comfortable with that, using wireless charging devices so they can get deployed more?
That's such a great question. I hear this all the time, and it's actually known as the field of electrophobia. Started, I believe, in Israel, where they used to have riots about cell phone towers. They were blowing them up. And in the UK, they've come out with a thing where 5G causes cancer. I would not worry about wireless charging, because when it comes to safety, and this is human safety, not product safety, there's two types of energy, which is ionizing fields and non-ionizing fields. Ionizing is when you vibrate the electrons 3.5 gigahertz. At that frequency, it generates lots of heat. And that's how microwave ovens work. It vibrates electrons. That's ionizing. X-rays are ionizing. Gamma rays be ionizing. Wireless communication is using RF. That's non-ionizing. And if people are so afraid of using 2.4 or 5 or any other frequency, then they need to find a place where there's no such thing as electronics. Because where you're sitting right now, you are being bombarded by tens of thousands of RF signals, wireless signals, telecommunication signals, commercial broadcast, AM, FM radio, aeronautical communication, lands, if you're in a building. Okay, what about your cell phones?
Right.
We live in an electromagnetic environment to where there's so many signals all present at the same time, it creates what's called broadband noise. And the specifications is to find that one narrowband spike within all of this noise in the environment, and that one spike could cause harmful interference.
Right.
But at the power levels we're dealing with, it's not a problem. There could be concern down at the 50 to 60 hertz for very high power. There's been some studies that it may cause the potential for childhood leukemia, but those studies are sort of inconclusive. But if you're worried about putting a cell phone to your head and getting cancer, then don't use a cell phone. And that operates at the exact same frequency as wireless.
Point. Great. Okay, well that helps some. We got one other question from the audience, is relating to FCC, part 18. Is that limited to a certain distance?
Well, the
part
FCC,
18?
the test for FCC is generally at 3 meters and 10 meters.
Okay.
The spec technically is at 10 meters. You can extrapolate it to 3 meters. But if you can't pick up the signal, you move the antenna into 1 meter, and then you do your calculation, which is pretty simple, 20 to the log of 10 over 1. You add that number to your reading, and now you get a correction factor.
Okay.
But that's testing the whole system. And if you're dealing with a small magnetic or inductive loop coupling, magnetic field, you're not going to see that field in the far field, I guarantee you. The only time you're going to see that is with maybe a magnetic loop or a near field probe that's only a centimeter or 2 away.
Yeah.
I know the tests are sort of ridiculous. You generate such low power, but the laws say you got to test. One time there was a device, a little wireless charging, a Qi, that was inside a semiconductor manufacturing chamber. That was huge. They had to take that through the whole regulatory process because it had communication, even though it's in an inch-thick aluminum enclosure utilized in an industrial environment.
Yeah. Okay. Well, thank you. Thank you for all this great insight. I think in the interest of time, we're going to have to move on to the next presenter. Thanks, Mark. So our next presenter is Dr. Rosita Teymorzadeh from Asbil Corporation. She received her PhD in microengineering and nanoelectronics. Her skills are focused in the fields of software development, algorithm and digital systems design, and embedded design. She's a senior R&D electronics and software engineer at Asbil. In addition, she has published several valuable technical books and papers, and she holds 9 US patents. Go ahead, Rosita. Rosita?
Sure, I'm sharing the screen. Okay. Okay, is the screen is visible, right?
Yeah, we just see your file
Okay.
directory.
Hi, everyone. This is Rosita.
We don't see the presentation though, Rosita.
Stop sharing. Is it visible right now?
Yeah, it is now.
Is it visible?
Yes.
Okay. Hi, thanks for inviting me for this webinar. I'm very interested to talk about the total wireless sensor for industrial sensor deployment. I'm a member of research and development at Asbil, and thank you so much again for giving this opportunity to me. Today, I would like to try to talk about factory automation and target application field. Here, we try to picture a wireless factory automations that deploy a large population of sensors for sophisticated sensing and control in the industrial and commercial infrastructures. This topic is the challenging task and it needs a lot of attention and background knowledge in order to design the whole system. The use of wireless sensor network for industrial application has attracted a great deal of interest. As-Bill makes a human-centered automation as the business activity that contributes to the sustainable development of society. Here is a model of factory automation with potential deployment of total wireless sensor. Easy installation is one of the goals in wireless factory automation model, and the flexibility for installing is required. Installation time should be minimized to keep customers' productivity, and hence we are developing the wireless solution. Among the available As-Bill product, we have selected distance adjustable photoelectric switch known as HP7 for further research and development. HP7 is just an example for wireless sensor, and it's used as a factory and picked up for demonstration because its application required low latency and high reliability. Also, the density in the communication area is more tight than outside field sensors. HP7 is capable of detecting objects in various heights and in the between of conveyor model for developing the wireless factory model. So, since we are talking about wireless factory automation model, it is very necessary to align our design with a sensor network application. There is a key design that I would like to concentrate on that to know how we can design a sensor to fulfill the requirement of wireless power and wireless data. Here is one of the most important key design is low cost and small sensor node. Compact and low-cost sensor devices are essential to accomplish large-scale deployment of wireless network sensor. In addition, a scalable architecture is necessary to develop flexible and scalable architectures that can accommodate the requirement of wireless factory automation in the same infrastructure field. Efficient protocol is one of the important things that sensor should communicate with wide range of devices in reliable protocol. And then number 4, localization. Sensor node should locally filter and process the data and make the ready data in order to send it to and communicating with others nodes. Energy design, efficient energy design. Energy efficiency is important to maximize the network lifetime while providing a required energy to others' sensor. In advance to that, the self-configuration, that means existing node can also be removed from the system without affecting other wireless sensor, or in other words, the system should be fault tolerant. And the last but not least is a security. When designing a secure mechanisms for wireless sensor network, both low-level and high-level security should be taken care of. So among these titles that I mentioned, we are moving to total wireless sensor concept. So perhaps we have worked and introduced a total wireless sensor by putting the sensor in the field in factory automations, and the concept of total wireless sensor comes on top of the wireless network sensor. We have wide range of the sensor in the field that power up wirelessly using the loop, and the loop will provide the wireless to the data signals, and all sensors with the receiver will receive power wirelessly and start functioning the performance. And while we are talking about wireless data at the last of the chain, we need wireless power at the beginning of the chain in order to run the whole system. On top of the wireless power source, we need to have localization that as I mentioned, all the sensors need to do computation before sending the data to the next level. And the reason for that is that not to waste energy and not to waste data processing on the space while we are doing the wireless data communication. The next chain after edge computing is the security. I believe if the engineer in the past, they knew the importance of the security, today they would change their design and the way that they design the sensor. And the reason is that we didn't take care of the security in the past. That's why we have a lot of issue today. We really need to take care of our data, protect it, and when we send it, we need to ensure that our data are traveling in a safe environment. And the last chain of our total wireless sensor goes to the wireless communication, and is the place that our data is ready and going to transfer wirelessly. There is a lot of protocol for wireless communication, and such as wireless personal area network technology that designed to reach only about 10 meters like Bluetooth. There is a wireless local area network that can deliver up to 200 megabit per second distance and up to 100 meter. There is a wireless metropolitan area network technology that delivers up to 75 megabit per second over wireless. And last layer is our wireless wide area network technology that can deliver up to 100 kilobyte per second over large service area or city or country. Depends on which protocol we are picking and depends on our application. The most important things that we need to take care is reliability. And that means that any data that we are sending, especially in industry level, all the data should receive without losing any information. That is a challenging task. And of course, the total wireless sensor should provide the API for industry monitoring system to troubleshoot and collect the log and to enable to necessarily monitor what the sensors are doing in the field. After this discussion, I can conclude my presentation based on the total wireless sensor have a lot of potential fields that need to be addressed. And one of those is the reliabilities and security that still is a challenging task. However, because of the diverse industrial application requirements and large scale of the network, several technical problems still remain to be solved, and we need to address it before the full deployment in factory automation system. So now, since we have a time limitation, I just open it for Q&A and pass the things to Jeremy.
Thanks, Rosita. That's great to see some good industrial applications of wireless power. One question is, what are the challenges that you're facing using wireless power in industrial applications?
Oh, that's a great question. I think it's the question that being alone through our presentation, and perhaps Mark answered it very clearly. What we have here is that we are talking about wireless data, we are talking about wireless power, everything that is in a space. There is a lot of noise that may affect the data that you are transferring. And in other words, also there is a limitation of the range that wireless may support. So by considering all this issue, the range and noise that is in the system, all the signal that is in the space, it's seeing the data coming to the receiver without affecting and without corrupting the data. That's a very great challenge task, at least in our processing. And perhaps it would be good to observe all the stage one by one to ensure that the data is still healthy and we can transfer it without any defect.
Okay, one other quick question. Can you describe how the edge device was powered wirelessly?
What we have here, we have a sensor that all the sensor they have in data generation, they have a receiver, and perhaps now our wireless power source is a looping that the wireless power generate a loop of power in the field. So each receiver that here is our H node and is HP7. When they connect to the receiver and they receive the signature from the wireless power source, they can get power up. So we assume that all of the sensors here, they have a receiver that match the signature sent by wireless power. And as long as they are located in that electromagnetic field, they will get power and they will start functioning.
Okay. Thanks, Rosita. Appreciate it. We're gonna move on to Shadi from Everactive.
Thank you.
Thank you. So I'd like to introduce Shadi Hawawini, who's the VP of Customer Experience at Everactive. He's responsible for ensuring a wonderful end-to-end customer experience that empowers customers to understand their business impact and take action. Shadi has over 15 issued and pending patents related to USB charging, power converters, and battery management, and holds an MSEE from Santa Clara University and a BSEE from San Jose State. Go ahead, Shadi.
All right. Yeah, great. Thank you, Jeremy, and thank you, everybody, and thank you for putting on this event, especially given the circumstances and the time. So Everactive, for those of you who don't know, we are singularly focused on enabling truly pervasive sensing. So really imagine sensors really in the environment around you. Our first focus is really in industrial applications, and we're big believers that the way in which you enable truly pervasive sensing is by removing the battery. So creating trillions of sensors that have no batteries in them whatsoever, and of course need to run off of harvested energy. So like Rosita, a lot of our focus has been in the industrial space, so we'll be touching on some of those themes, but a lot of the material is applicable more broadly, so to consumer applications, think smart XYZ application. So, COVID-19 has actually been a really interesting use case. A lot of people are describing this as the new normal. And what does that really mean? People talk about lockdowns and working from home, less time to work. I have a fake background. I'm in my garage because I have 3 children and they don't let me work. So trying to carve out time is always a challenge. We have less information, less interactions, and can be, generating less revenue. And really what we need to know is, we need to know what's going on, even if we're not in the office or in the facility. We need to try to save time and money and to act more efficiently. Really, these are the goals that we try to incorporate. And, really for industrial applications, it's really trying to know what's happening with your assets. In a big industrial facility, you're going to have tens of thousands of assets that generally you have people monitoring in a very manual process. And sensors that you do deploy are really only limited to the most significant ones. So you have lots of sensors, continuous flows of data. You need data that matters, and you need data that gets to you. And we really believe at Everactive that the new normal needs pervasive remote monitoring. It's real-time visibility across all assets, and it requires cost-effective deployments. It requires continuous data streams. It requires end-to-end solutions. So like Rosita touched on, simple to install, low cost, doesn't take a lot of time to do, it just should work and should be very secure. And then of course we believe maintenance-free batteryless devices. And this of course can only be enabled with energy harvesting. But we talk a lot about this being the new normal, but the reality is a lot of these forces were already in effect. Remote monitoring concepts have been discussed in sort of the Internet of Things or Industrial Internet of Things, Industry 4.0. There's a real, what we call skills gap in industrial applications. A lot of folks with very unique knowledge sets are retiring out of the workforce and they need to be backfilled. And oftentimes there aren't people who are skilled to actually take on those tasks. So that has to be augmented with technology. And so we really view COVID-19 not so much as being really the new normal and a new state of affairs, but it's really the catalyst to accelerate a lot of these initiatives that had already begun and already had a fair bit of momentum. And we believe that batteryless truly makes remote monitoring possible and at scale. So not talking tens or even hundreds, but thousands or tens of thousands of sensors. So the question really is, well, how do you replace batteries from wireless sensors? How do you enable all of these? How do you enable self-powered operation? And the way that oftentimes these systems are viewed is you have your input, you have your harvesting power, which is topping off your storage energy. Generally, it can be a battery, or for batteryless, of course, it's a supercapacitor. And then you have consumed load power. So when you're taking action, reading from the sensor, doing continuous processing, you're consuming power. And those two need to, at a bare minimum, match. And ideally, you want more harvested power than you are expending in consumed load power, because you assume that harvested power is not always going to be there. And so, you know, the goal again is to try to fill your tank as much as you can. So you want high harvested power and you want very low load power. Now, at Everactive, what we've done is we've taken the approach that there are a lot of energy harvesting options. And in fact, to do more with that, you have to reduce the power envelope. So for us, we've really taken the approach of taking off-the-shelf harvesting technologies. And, you know, Jeff had alluded to the ones that are readily available. A lot of people talk of indoor, outdoor solar, temperature differential, so a thermoelectric generator, vibration, and vibration really comes in a couple of different forms. You have things that are better suited for higher frequency type applications, and then similarly you have ones that are think voltage-induced EMF, or lower frequency, where you have a magnet going through a coil. And then you have wireless power, of course. And to each of these, there are benefits and there are challenges. And really, wireless power can address some of the deficiencies that other harvesting options do have. So for example, if your sensor is in a box and that box is on the shelf for a while, it's dark in that box, so solar is not a good option. It has no temperature differential. It's been on that box for a while, so thermoelectric generator is not a good option. And it hasn't moved, and therefore vibration isn't a good option as well. However, it can introduce significant additional design complexity. Generally speaking, for wireless power transfer, the wireless range of the power transfer could be significantly less than the wireless range of communications. So that can be the limiting factor. So if your goal is to deploy pervasive sensing and you're trying to attach thousands of sensors to a single gateway, if the limiting factor is then the wireless power range from that transmitter, it's going to limit the scale of what you can actually deploy. And then the challenge, of course, is how do you piggyback onto other existing wireless standards such that you're sort of harvesting from the ambient. So Niraj talked a lot about setting up separate transmitters that act as power stations, in effect, requiring separate hardware. It's not unfeasible. In fact, a lot of people do similar types of things with the wireless protocols themselves, but it, again, introduces additional design complexity. So really the way that we view it is wireless power is a great tool in the tool chest. When you're designing batteryless systems that are powered solely off of harvested energy, you really need to try to identify what is the right solution for the right application. And the reality is that it may be multiple sources. It might be wireless coupled with solar, for example, or solar coupled with thermoelectric generators. But the core of it is really to understand what are the use cases of the product. So it's really trying to be as empathetic as possible to what the users would need to use the product and what is the environment like. Because again, all of these have deficiencies. Indoor and outdoor solar, lights are going to be on maybe 5 hours in a day or 8 hours in a day, 10 hours in a day in a facility. It's oftentimes very directional. So how do you then account for mounting it such that you get good visibility on the light source itself? Similarly, for thermoelectric generators, you apply temperature on the hot side of a thermoelectric generator, and right away you'll harvest a lot of power. But the reality is you have radiated heat, which will be self-heating the cold side. So after an hour or so of operation, the thermo differential you thought you had has now gone to zero, and you have very little power coming in. Similarly for vibration, things move and don't move. So you have to deal with a lot of these intermittent cases, and therefore you really need to understand what is the use case, what is the application, how will this product typically be used. So in the interest of time, that's the material I have. Please, any questions, I'm happy to answer. Thank you.
Thanks, Shadi. I appreciate that. I guess one question that has come up is, do you have a feel, and I know this is probably a large topic, but about the economics of deploying this energy harvesting?
Yeah, certainly. Well, the industrial space is unique because the costs associated with battery replacements is really high. And so if you were to compare the costs associated with adding an energy harvester relative to someone going on, say, a yearly or every other year cadence to actually replace the batteries, the cost is actually significantly lower for the energy harvesting case. Energy harvesting sources themselves, thermoelectric generators, for example, are still relatively expensive, especially when compared to, say, for example, a AA battery. But the other consideration in industrial environments is these are often put into hazardous locations as well, meaning they have to be rated for something called explosion proof. And in those environments, AA, AAA batteries generally don't suffice, and you have to use more exotic materials that are safer materials. And so similarly, it actually means that energy harvesting is actually a significantly less expensive way to deploy in these environments.
Okay, thanks. That's really useful. So this concludes the presentation part of our webinar. I think there's a few additional questions from the audience that I'd like to open up to the whole panel. And there's one that came early on. It was addressed to Jeff, but I think it might apply to Niraj as well. Do you see companies doing beamforming, power delivery, and cellular or wireless LAN communication together? So basically wireless power and communications together. Maybe Jeff or Niraj or both of you guys could take that.
Yeah, I think Niraj probably can take that because Energis will be my no or suggestion.
Yeah. Thanks, Jeff. I think this is more like a product question, but that's how I look at it. If you look in the beamforming, so I think the question is two-part. Should you use beamforming and non-beamforming technology for RF power transfer? That's number one. And number two is that can you coexist in the same band for data as well as power? A lot of people talked about it earlier. Let me address both the questions separately. The first is, I think beamforming requires a length of the array or the width of the array. That can be a constraint in certain use cases. It might be okay in the non-consumer market, but in a consumer market, you may be limited. For example, a small speaker trying to put an array there may not be a good idea. So if you look into about 2 weeks back, we announced FCC approval for a device which is up to 30 centimeter that can actually use single PA, single antenna. It's non-beamforming version of our technology. That doesn't mean it replaces. In my view, beamforming has application for a certain part of the market because of the size, complexity, and cost, and the non-beamforming has the application. The second is can you communicate in the same band? My answer is no, because I think if you look into the maximum power allowed in part 15, if you have to communicate in the same band, you have to follow part 15. And part 15 limit is a 4 watt EIRP, which is what is required. And if you start to put that in the link budget table for 4 watt at 2.4 or 5.8 and think how far you can go, they're very limited. So if you look into our implementation, we have a separate frequency for the power. We are using 900 for most of that. And then we use 2.4 BLE for the communication. I do not suggest trying to put in the same band because then you'll be limited on the transfer power.
Okay, thanks. That's great information. Another question, and we're going a little bit over time, so probably this may be the last one unless I get more in from the audience. What is the maturity of wireless power for making wireless sensor networks feasible and practical? So I think just overall, how mature is this for implementing into systems? And it's something that somebody might want to take.
Yeah, I think it goes. Yeah, I think it goes to wireless network sensor. What we have today, we are in the research and development, but very, very stable and perhaps very close to going to deployment. The test, most of them is passed. We're just making sure that it's passed all the test cases and push it to the next phase.
Okay, great, thanks. So I think there's an awful lot of great content here and topics that we can probably continue into a future session. So maybe we should do a stay tuned, same bat time, same bat channel in a future future meeting. Thanks, everybody. We really appreciate your participation in today's webinar. Please join us for our next webinar in June that's going to highlight a new interesting topic in millimeter wave and terahertz technologies. We're going to set the date within the next several weeks and send out a notice. So if you haven't already signed up for our newsletters at www.wca.org, please do, so you can get updates for these things. So we'll send out more information then. Also, just one final note, WCA is growing. We're adding more volunteers, more board members. We're always on the lookout for additional people to help out with things, and also recommendations for new topics. So please reach out to us and either join our team or keep communication with us if you think this is valuable to you. Thanks again, and if there's any final comments from the panel, feel free. Otherwise, we'll close this out. Okay. Thanks, everyone. Have a wonderful evening, wonderful weekend, and stay safe out there.
Thank you, Jeremy.
Thank you,
Okay.
Jeremy.
Thank you. Bye-bye.
Bye.